Welcome to the lecture on solving systems of equations. A system of equations is basically any collection of equations. Typically we will be solving 2 by 2 systems or 3 by 3 systems. A 2 by 2 system is 2 equations in 2 variables, and a 3 by 3 system is 3 equations with 3 variables. When we solve a system of equations, what we're looking for is a point or set of points that makes all the equations true at the same time. So we're going to start by solving 2 by 2 systems of linear equations. So we're going to be talking about 2 lines. And when you think about 2 lines and you're trying to find the solution that makes them both true at the same time, there are 3 possibilities that could happen. The most common possibility is if the 2 lines were to intersect, and your solution would be that intersection point. So that would be a point that's on both lines at the same time. Another possibility with 2 lines is that they could be parallel lines. And if that's the case, there's no intersection at all, so our solution would be the empty set. And then the third case, which isn't quite as common, is if you have 2 equations that may look initially very different. However, when you go to graph them, they turn out to be coinciding lines. So they turn out to be the same line right on top of each other. And in that case, every point on the line makes both equations true since they are both the same line. So your solution is going to look like the equation of a line. And we kind of have a fancy way of writing that with these curly braces, parentheses x comma y, colon, and then you write whichever equation of your line that you want. You can pick that. So your 3 possibilities would be intersecting lines, which have a single point as an answer, parallel lines, which have no solution, or coinciding lines, which would be the equation of a line for your answer. And we will see examples of all 3 of these. So there's several different ways to solve systems of equations. The first method that we're going to use is to solve a system graphically, and to do that you're going to just take each equation of your line and you're going to graph them right on top of each other, and you're looking for that intersection point. So if we start with this first equation, x plus y equals -5, and we want to graph this, very simple way to graph this because it's in that standard form already. We could find the intercepts. So we could make a little xy table and find the 2 zeros. So we're going to let x be 0, and we're also going to let y be 0. Now if we let x be 0, then this x goes away, and all we would have left is y equals -5. If we let y be 0, then the y goes away, and all we would have left is x equals -5. So both intercepts are at -5. So 0, -5 would be this y-intercept down here, and -5 comma 0 would be this x-intercept, and my line is just going to be connecting these 2. Okay, so now let's graph the other equation, -2x plus y equals 1. You could also do this with intercepts, but just as an alternative, you could also solve this for y. It's very easy to just add 2x over to the other side, and we would get y equals 2x plus 1, and that puts the equation of the line into slope-intercept form. So your slope m is 2, or 2 over 1, and your b is this y-intercept over here, +1. Remember that slope we're going to think of as rise over run, and 1 is the y-intercept. So when we go to graph this line, you want to start with your y-intercept, which was at 1, put a dot, and then you can use your slope from there. So starting at that 1, our slope was a rise of 2, so up 2 over 1. And there's our second dot. And now we're just going to connect the 2 dots together, and we get a line that looks like that. And what we're looking for when we graph a system of equations like this, the solution is going to be the intersection point, which we can see right here is going to have coordinates of -2, -3. So -2 comma -3 would be your solution. Now the downside to solving a system graphically is that lines can be crooked. You can have solutions that don't come out to be very nice numbers. If these were fractions or decimals, we wouldn't be able to tell what those answers were exactly from a graph. So a graphical solution isn't the most accurate way to find a solution, but it is very visual, so it has that going for it. To give a little more accuracy to our solutions, we're going to learn two other methods. The next method is called the substitution method, and in this method you're going to take your two equations and you're going to pick one of the equations, whichever one looks easier, and solve it for either x or y, again, whichever one is easier. So for example, if I look at this system right here, it looks pretty easy to solve the second equation for y because all I would have to do is add 8 to both sides. So y would equal 4x plus 8. I'm going to put a box around that because we're going to have to come back to that later. And once you've solved one of your equations for either x or y, then step 2 is going to be to take that whole expression for what in this case y was equal to and substitute it in for y into the first equation, the equation you haven't used yet. And I'm going to want to wrap this in parentheses so that I substitute it in correctly. So basically we're going to rewrite this top equation with y substituted in with 4x plus 8. So the new equation would look like negative 3x minus 5, and instead of y we're going to put parentheses 4x plus 8 equals negative 17. If you've done this correctly, then you should now have an equation that only has one variable in it, only x's or only y's. And so that should be something that you can solve. All we have to do here is distribute our negative 5 across. So we're going to get minus 3x minus 20x minus 40 equals negative 17. I have a couple like terms here, so negative 3 and negative 20 is negative 23x. And if I add 40 to the other side to get my numbers together, negative 23x equals 23. 40 minus 17 is 23. So if I divide both sides by negative 23, I get x equals negative 1. Put a circle around that. Now that is part of our answer. Remember, when you're giving a solution to a system, it has two parts. It has an x and it has a y. So we just found out what x was. We now need to find out what y is. So that's where we're going to go back to our box over here, and we're going to substitute in negative 1 for this x. So this is going to become y equals 4 times negative 1 plus 8. So negative 4 plus 8, and that gives us y equals 4. So our solution, usually when we write a solution to a system, we write it as an ordered pair. Always put x first and then y. So this would be the solution negative 1, comma 4. Okay? Let's try that again. In the next example, same thing. You want to take your equations, look them over, and see what would be easiest to solve for. In this first equation, we already have y solved for. It does have a fraction in it, which may bother some people, but since it already is solved for y, I'm going to go ahead and use it. And that means in the second equation, the one we haven't looked at yet, we're going to substitute in for this y 1/7 x plus 3. So all of this wrapped in parentheses is going to get substituted in for that y. So let's rewrite the second equation. X minus 7 parentheses 1/7 x plus 3, and that's supposed to equal negative 21. So now we have a new equation with only one variable x. Now to solve, we're going to want to distribute our negative 7 across, so we'll get x minus 7 times 1/7. Those two 7's cancel out, so this is just going to be a minus 1x or minus x. Negative 7 times positive 3 is negative 21. And if we go to combine like terms, we see that these two x's cancel each other out. And that's kind of a strange thing that happens. So you want to make sure you look to see what's left over. notice that we still have a minus 21 left on the left side and a minus 21 left on the right side. Now whenever you have an equation or system like this where the variables are canceling themselves out so that there's no variables left, this is going to be one of those special cases. Remember that when you're solving a system of 2 by 2, system with 2 equations, 2 variables, 3 things could happen. You can have an intersection point, like the last example. You could have parallel lines, or you could have coinciding lines. So in this example, based on what's left, negative 21 does equal negative 21, so that's a true statement. So out of our 2 special cases, parallel lines or coinciding lines, which case must this be? Well, it has to be the coinciding lines because we want to get a solution here. And what this true statement says is no matter what I plug in for x, we're always going to get a true statement. In other words, these 2 equations are actually the same exact equation, just written in different forms. You could probably visualize that if you were to take this top equation, multiply through by 7 all the way across, and then just to rearrange some terms, you would end up with this second equation. So these are exactly the same line. So your answer here is that this is a coinciding lines case, but what you want to actually write down for your final answer should be the equation of the line, because every point on the line is going to be shared by these 2 equations since they turn out to be the same line. So our answer is going to look like this. We use this kind of fancy notation, a curly brace, parentheses x comma y, colon, and then after that colon, pick either equation of your line to write down. It doesn't matter which one because they're the same. So I'm going to use the second one here. X minus 7y equals negative 21. And then you just close this off with that curly brace. And what this means is that we are giving for our answer the set of all x comma y's such that x minus 7y equals negative 21. That's what this notation really means if you were to say it out loud. So we're basically saying that every combination of x and y that satisfy x minus 7y equals negative 21 is going to be our solution. Okay, let's try one more example with substitution. On the next example, remember you're trying to find one variable that looks easy to solve for, and in this top equation, y is already solved. So I'm going to go ahead and put my box around that equation, and I'm going to substitute in 2x minus 3 right in for this y. So rewriting the second equation, this becomes 2 parentheses 2x minus 3 minus 4x equals to 4. And if we distribute our 2 across, we'll get 4x minus 6 minus 4x equals 4. And when we go to combine like terms, our 4x's cancel out, and we get negative 6 equals 4. So when you have the case where the x's or the y's are canceling out, then you want to look to see what's left over. Either it will be a true statement, like the last problem, or a false statement, like this problem, since negative 6 does not equal to 4. Now, if it's a false statement, that's basically saying no matter what we pick for x, there's no way this equation is ever going to be true. So there's no x's that are going to work. So our solution here is no solution. And if you want to visualize what this is, these would be parallel lines. These 2 equations, if you were to graph them, look like the same exact line, but they have a different y-intercept. So they're parallel and they would never intersect. So a true statement, like in our earlier example, would give you coinciding lines, and your answer is going to be the equation of the line. A false statement, like our last example, is parallel lines, and your answer is going to be no solution. Okay, so we've talked about the graphing method, we've talked about substitution method, now we're going to talk about the method called elimination. Now, elimination is a really useful method. We're going to use this not only to solve 2 by 2 systems, but also 3 by 3 systems. And it's really useful because most of the time your equations are probably going to be written in standard form, which is that pretty form, ax plus by equals to c. So most of the time you already have both equations in that form, and then it's going to be easy to do your elimination because your x's will be lined up, your y's will be lined up, and your numbers will be lined up. So this is how elimination works. First of all, you want to make sure that your x's line up, your y's line up, and your numbers line up. Once they do, you're going to look at either your x's or your y's and decide which one you want to eliminate. And what you're looking to do for that, in order to eliminate a variable, you want the coefficient out front of that variable to be the same number in both equations, but opposite signs. So if I wanted to get rid of x's, I already have a -2 in the second equation. I would need to have a +2 in the top equation. Then those numbers would be the same but opposites. If I wanted to eliminate y's, they both already have a +1 in front. If I just make one of them negative, then they would be opposites. So in that respect, it looks like putting in a negative isn't that hard to do. So let's go ahead and eliminate y. Now to eliminate the y, we need to make these signs become opposites. So we're going to take one equation, it doesn't matter which one, and we're going to multiply through by -1. I can't just put a minus in front of the y because that wouldn't keep the equations equivalent. So to keep the equation balanced, we have to multiply the entire equation by -1 so that it's equivalent to the original one I was given. So let's go ahead and multiply this top equation through by -1. That's going to give me -x, -y equals +5. And the second equation I'm going to leave exactly the same, but I'm going to line it up underneath my top equation. Now if you have them lined up, then you should be ready to add down the columns right away. -x plus -2x is -3x. Because we made the signs on the y's opposites, these y's should always cancel out. And on the right side, 5 plus 1 is 6. So based on this elimination, after eliminating y, you can see that you're left with a really easy equation to solve for x. All we have to do is divide through by -3. So x is -2, and I'm going to put a circle around that. There's part of my answer right there. Now, to get the rest of my answer, remember we need to find out what y is. So unlike substitution, there's no easy boxed equation that we can go back to find out y right away. What we have to do is go back to either one of the two original equations and substitute in -2 in for x and solve for y. So usually I try to pick the equation that looks easiest to work with, and in this case that might be this top one just because the coefficients of x and y are 1s, so it's pretty simple. So I'm going to take that equation, I'm just going to recopy it, and now I'm going to substitute in -2 for that x. And if I solve this for y by adding 2 to both sides, we get y equals -3. So our two solutions are going to be -2 for x and -3 for y. So here's our final solution. Okay, so that's called elimination. Let's try it again. On this next example, we are going to line up our x's, our y's, and our numbers, and they already are here, so we're ready to go. Now what we want to do is decide which variable looks easier to get rid of. Should I eliminate x's or should I eliminate y's? And in this problem, they both look equally the same difficulty. Sorry about that, my pen is acting up on me. So if I want to eliminate x's, for example, I have a -4 coefficient here and a 2 coefficient here. If I were to take this 2 and multiply it by 2, then I would make a 4 here and a -4 here, and that's exactly what we want. The same number but opposite signs. So I'm going to have to take 2 times the entire top equation in order to eliminate the x's. So let's do that. If we multiply through by 2, we'll get 4x minus 6y equals 14. Underneath that, I'm just going to recopy the second equation. And now we're ready to add down. Because we made the coefficients in front of the x's opposites, these should always cancel out. Notice in this problem, the y's also cancel out. So what's left on this left-hand side of the equation? Nothing, just a 0. On the right-hand side, be careful. These are both 14s, but they're not opposites, so they don't cancel out. 14 plus 14 is 28. If your variables all cancel out like this, then remember you want to look to see what's left. Either it's a true statement or a false statement. And in this case, 0 does not equal 28, so this is a false statement. So what does that imply? Remember, that means we're talking about parallel lines. There's no x or y that's going to make 0 equal 28 ever. So there's no solution. And that would be our final answer. Okay, let's try one more. Okay, on this next example, when we try to eliminate either x or y, they're already lined up. To get x's eliminated, since I have a 4 and a 3, you kind of want to think of what a common denominator might be, or in this case a common factor. 12 is divisible by both 3 and 4. So I could fairly easily make these 12s, but I'd have to multiply both equations by something. If I wanted to eliminate y, then I'd probably need to get 6's out front, since 2 times 3 gives me 6. And again, I would have to multiply both equations by something. So it's going to be equal amounts of work to eliminate either x or y. So here you just want to take your pick. Let's say that we want to eliminate x. Then I would need to multiply the top equation by 3, so that 3 times 4 will be 12, and the bottom equation by 4, so that 4 times 3 would be 12. And then remember, not only do we want these to be 12s, but we want them to be opposites. And right now they would both be positive. So pick one of these to be negative. I'll just make the bottom one a negative. So let's multiply the top equation by 3. That's going to give me 12x plus 9y equals 3. Multiplying the bottom equation by minus 4 gives me negative 12x minus 8y equals negative 8. And I should be ready to add down. 12x minus 12x, those should cancel out. 9y minus 8y is 1y, or just y. And 3 minus 8 is negative 5. So here's my y. We now know y. So what we need to do next is find x. So to find x, you go back to your original two equations, pick the one that looks easiest to work with, and substitute in negative 5 for y, so you can solve for x. Now both of these look the same equal difficulty level, so I'm just going to take the second one here. Let me recopy it, and we're going to substitute in negative 5 for that y. So this becomes 3x plus 2 times negative 5 equals 2, or 3x minus 10 equals 2. If I add 10, get 3x equals 12, divide by 3, so x equals 4. So my final solution is 4 comma negative 5, x comma y. Okay, so we have graphing, we have substitution, and we have elimination. Those are your three techniques that you can use when you're solving a 2x2 system of equations. Now what we're going to move on to next here to finish off is solving 3x3 systems of equations. And when you're doing a 3x3 system, usually we stick with elimination. You could possibly do it with substitution, but most of the time the equations aren't set up to work quite as nicely with elimination or with substitution. So usually elimination is what we're going to do. And because we now have 3 equations in 3 variables, elimination is going to be a little bit more involved, and this is going to be quite kind of a lengthy process when you're trying to solve a 3x3 system. So the key to doing these is going slow, being organized, and just making sure that you're being very careful with your arithmetic as you go throughout the problem, because any little mistake you make is going to obviously throw off your entire final solution. And these problems can take a little time to do, so you want to try to get them right the first time. So here's my example. in these elimination methods, you want to get all your x's lined up, all your y's lined up, and all your z's lined up. Now notice here we're starting with a 3 by 3 system. The goal for solving these is typically to take two equations at a time and eliminate a variable from them, and then take two more equations and eliminate the same variable from them, so that you can take your 3 by 3 system and narrow it down to a 2 by 2 system. And then you're going to use the elimination that we just talked about in the last few examples to narrow this down to a 1 by 1 system, which is just going to be your answer, like x equals 5 or y equals -2. Once you know either x, y, or z, once you know one of the variables, then you're going to back up one step back to that 2 by 2 system to find a second solution, and then you're going to back up all the way to the beginning to find your third variable. So that's kind of the overall process. So let's see how this is going to work. First thing we want to do is look over our equations over here and decide which variable looks the easiest to eliminate. Here, these x's are already opposites, so that's kind of nice. For the y's, the two y's are the same. We would just need to flip some signs around, so that's not too bad. The z's are all different. So most likely, I would probably choose to eliminate the x's first, just because equation 2 here and equation 3 are already ready to go. So what we do when we eliminate x is we want to make sure that we pick two equations and eliminate x from them. So let's go ahead and take equation 2. I'll label these 1, 2, and 3. Let's take equation 2 and equation 3, and I'm just going to recopy them down below. So equation 2 is x plus y minus 2z equals -8. And equation 3 is -x minus 2y plus 3z equals 13. If I add down, the x's cancel each other out. Y minus 2y is -y. -2z plus 3z is 1z, or just z. And -8 plus 13 is 5. So now this becomes the first equation in our 2 by 2 system. What we need is a second equation that also has y's and z's in it, so that we can then proceed to our 1 by 1 system. So how do we get a second equation? Well, we've already used equation 2 and equation 3. We haven't used equation 1 yet. So you have to use equation 1 in the next step, so that you're making sure to use all three equations. Since equation 1 has a 3 coefficient in front of that x, let's take equation 3 times 3, so that this will get a -3 in front, and that way we can eliminate the x's from equations 1 and equations 3. So in other words, I'm going to take equation 1 and 3 times equation 3. So let's recopy equation 1. Let's recopy what we get when we multiply through by 3 times this third equation. So 3 times -x is -3x, 3 times -2y is -6y, 3 times 3z is 9z, and 3 times 13 is 39. Now we should be able to add these down and cancel out my x's. -2y minus 6y is -8y. Z plus 9z is 10z. And 9 plus 39 is 48. That now joins my other equation that I got earlier, so I'm going to line it up underneath, and here is now my new 2 by 2 system of equations. So now we're going to treat this just like we did in the last section of examples, where we want to eliminate the same variable from both equations, so we could eliminate either the y's or the z's, and it doesn't matter which one you choose to do. Let's say that we wanted to eliminate z. Okay, so if we want to eliminate z, then I need to get a -10 in front here. So let's multiply this top equation by -10, And if I do that, negative 10 times negative y is positive 10y. Negative 10 times positive z is minus 10z. And negative 10 times 5 is negative 50. So that's my new top equation. The bottom equation I'm going to leave alone, just line it up. So minus 8y plus 10z equals 48. And now we should be able to add down. 10y minus 8y is 2y. The z's cancel out. Negative 50 plus 48 is negative 2. If I divide through by 2, I get y equals negative 1. And that goes to my 1 by 1 system. So now we know what y is. So how do we get x and z? Well, only one of those is something I can find next. If you look back at your 2 by 2 system, the only variables used in that 2 by 2 system are y's and z's. So if I know y, I can determine what z is. So you have to find z next. So you take either of these two equations from your 2 by 2 system. I like to pick the easier one, which would probably be this top one. So I'm going to recopy it. And now we're going to substitute in the value of y. So negative 1 becomes positive 1. And if I subtract 1, we get z must be 4. So I know y, I know z, now I need x. So how do we get x? Well, we back up again. When we knew y, we backed up one step to get z. Now we're going to back up one more step to get x. So we're going to have to go all the way back to the beginning. Use an equation over here that looks easy to work with that you're going to need to use to solve for x. So maybe this middle one right here. And I'm going to recopy it. X plus y minus 2z equals negative 8. And we're going to substitute in 4 for the z and negative 1 for the y. So we get x minus 1 minus 2 times 4 equals negative 8. So x minus 1 minus 8, which becomes x minus 9. And if I add 9 to the other side, negative 8 plus 9 is 1, so now we know x. So our final solution, instead of being an ordered pair, it's going to be an ordered triple because I have x, y's, and z's. You want to put x first, so x was 1, then y, which was negative 1, and then z. So my solution is 1, negative 1, 4. Okay? So there's a lot of work going on here. It's easy to get confused and kind of know where am I headed, what am I supposed to do next. It's easy to get lost a little bit. So you really have to keep yourself organized and remember that we're taking a 3 by 3 system, narrowing it down to a 2 by 2 system, narrowing that down to a 1 by 1 system, and then we back up to the 2 by 2 system to get our second variable, and then we back up to the original 3 by 3 to get our third variable. Okay? So we're going to try a couple more examples of these. Let's take a look at the next one. So here's my 3 by 3 system. First thing we want to do, they're all lined up, x's, y's, and z's. So now we just want to decide which variable looks easiest to eliminate. So if you look at your x's, your y's, and your z's, they all kind of look like they're going to have the same amount of work involved. So, you just kind of want to take your favorite here and eliminate it. If I look at these, I'm going to maybe choose y just because I have a coefficient of 1 here, so that's easy to multiply through by stuff to get the coefficient that I want. So I'm going to eliminate y initially. So if this is equation 1, equation 2, and equation 3, then what I could do is take equation 1, which has a negative 2 in front, and add that to 2 times equation 3. That way I'm going to get negative 2 and a positive 2. So let's take equation 1 and 2 times equation 3. So if we do that, recopying equation 1 unchanged is minus 6x minus 2y plus 4z equals negative 2, and equation 3 times 2 turns into a 6x plus a 2y minus a 4z equals to 4. If I add down, the x's cancel out, the y's cancel out, the z's cancel out, so everything on the left side canceled out, so the only thing that's left on the left side is 0. On the right side, negative 2 plus 4 is positive 2. Remember, whenever all your variables cancel out, you either have a true statement or a false statement. This is a false statement. So what does that imply? It means no matter what I pick for x, y, or z, there's no way that I can get 0 to equal 2. And so there's no solution that's going to work. So this was actually an easy system because we got that false statement right off the bat, and so we know that there can't be any solution to this system at all. Okay, so anytime you end up with all your variables canceling out and a false statement, then you can immediately write no solution and you're done. You don't have to do any more work. Alright, that one was an easier one. Let's try a harder one. Okay, on the next example here, if you look closely at your system, you'll notice that the middle equation has only two variables in it, x minus z equals 16. So let's take the help where we can get it and immediately use that second equation as one of our 2 by 2 systems. And that means what we're going to have to do over here is take equation 1 and equation 3, the ones we haven't used yet, and we must eliminate y because in this equation over here there's no y, and we want our answer to match that. So if there's no y in this equation, then we want to make sure we're getting rid of y over here as well. So we must eliminate y. In order to do that, I have a 3 up here. I need to get a minus 3 down here. So let's take equation 3 times negative 3. So we're going to do equation 1, and we're going to do negative 3 times equation 3. So let's just recopy equation 1, and then underneath it, we're going to write down what we get when we multiply the third equation through by negative 3. So that's going to give me negative 15x minus 3y minus 9z equals negative 3. If we add down, 7 minus 15 is negative 8x. The y's cancel out. Z minus 9z is minus 8z. And negative 33 minus 3 is negative 36. So this now joins my other 2 by 2 equation. And now we have our 2 by 2 system right here to work with. Okay, so once we have y's eliminated, now we want to eliminate either x or z from this 2 by 2 system. So pick your favorite. They're both going to be the same amount of work. Let's say that we eliminate x. So if we want to eliminate x, then I'm going to have to take 8 times this top equation. So that's going to give me 8x minus 8z equals 8 times 16, which turns out to be 128. And now if I recopy the bottom equation underneath, minus 8x minus 8z equals negative 36. When I add down, the x's cancel out. The z's don't because they're both negative, so this becomes negative 16z. And 128 minus 36 turns out to be 92. Now we can divide through by negative 16, and 92 divided by negative 16 doesn't go unevenly. Let's go ahead and see what that is. If we do 92 divided by negative 16, we get negative 5.75. So z is negative 5.75. So we get a decimal, but it's not too terrible of a decimal. So that is part of our 1 by 1. There is the value of z. Now what variable must we find next? If you look back at your 2 by 2 system over here, it only had x's and z's in it, And since I know the value of z, I should be able to find the value of x. So you have to find x next. Out of these two equations, the top one looks much easier to work with. So I'm going to use x minus z equals 16, and I'm going to substitute in now my value of z. So x minus negative 5.75 equals 16. Double negative becomes plus. And now to solve for 16, we're going to want to subtract negative 5.75. So if we take 16 minus 5.75, we get 10.25. So x is 10.25. We know x, we know z, now we need y. To get y, the third variable, you have to go all the way back to your 3x3 system. I obviously can't use the second equation because there's no y in it. So out of the first one or the third one, I kind of like the third one best because it has a coefficient of 1 in front of that y. So I'm going to use that. So let me recopy it. And I'm going to substitute in 10.25 for the x. And I'm going to substitute in negative 5.75 for my z. So if we do 5 times 10.25, we get 51.25, and 3 times negative 5.75 is negative 17.25. So this is going to be 51.25 plus y minus 17.25 equals to 1. And if we do 51.25, whoops, typo there, 51.25 minus 17.25, that gives me 34. So this minus this is 34 plus y equals 1. Subtract 34 and I get y equals negative 33. So my final answer, x was 10.25, y was negative 33, and z was negative 5.75. And here's my final order triple. Now this solution did have a couple fractions in it. Typically, instructors will try to give you examples or problems on tests and quizzes that come out to be whole numbers. So if you are getting decimals or fractions that are really strange, then you're probably doing some arithmetic mistakes. So you want to double check your work. All right, our last example. Okay, our last example. 3x3 system. Looking at my x's, my y's, and my z's, we want to pick one that looks fairly easy to get rid of. I might want to eliminate, let's say we want to eliminate z's. Okay, so let's eliminate z's. If this is equation 1, equation 2, and equation 3, to eliminate z, I could take equation 1, which has a minus 3, and 3 times equation 2, so that I get 3's here, but opposite signs. So let's do equation 1 and 3 times equation 2. So equation 1, unchanged, is 2x plus y minus 3z equals negative 4. Equation 2 gives me 12x minus 6y plus 3z equals 27. If we add down, we get 14x minus 5y. These cancel out, and 27 minus 4 is going to give me 23. So that becomes the first equation in my 2x2 system. Okay, now I need another one to join it. I used equation 1 and equation 2 last time. I haven't used equation 3 yet, so I must use equation 3. And in order to use that, it has a minus 2 in front of that z. I'm going to have to take equation 2, maybe, times positive 2, and that way these will be 2's but opposites. So we're going to take equation 2 times 2 and equation 3. So 2 times equation 2 turns into 8x minus 4y plus 2z equals 18. Equation 3, unchanged, is 3x plus 5y minus 2z equals 5. Adding down, I get 11x plus y, the z's cancel out, and 18 plus 5 is 23. So that joins my other equation, and now I have a 2 by 2 system. Looking at this 2 by 2 system, should I eliminate x's or y's? Y's look much easier. All I'd have to do to eliminate y is multiply this second equation by 5. So let's go ahead and do that. The top equation stays unchanged, and the bottom equation becomes 55x plus 5y, and let's see, 23 times 5 is 115. So when we add down, we're going to get 69x, the y's cancel out, and when I add down here, I get 138. And then if I divide both sides by 69, 138 divided by 69 gives me 2, a nice whole number. So x must be 2. That's going to go over here in my 1 by 1 system. Now if I know x, what variable must I find next? If you look back at your 2 by 2 system, it only had x's and y's in it. So since I know x, I'm going to have to find y. And again, this second equation here looks the simplest because the coefficient of that y is 1. So let's use the second equation. Substitute in 2 for x. 11 times 2 is 22. And if I subtract 22, that tells me that y must be 1. So I know x, I know y. Now I have to find z. To get z, you have to go all the way back to the original equations. Pick the one that has maybe the simplest z term, which would be the second one. So I'm going to use the second equation, recopy it, and substitute in 2 for x, 1 for y, and we're solving for z. 4 times 2 is 8. 2 times 1 is 2. 8 minus 2 is 6. And if I subtract 6, I get z is 3. So my final solution, x was 2, y was 1, and z was 3. Alright, that concludes our lecture on solving systems of equations. Good luck.